Lecture video for February 24th through 25th. Get your notes out. Let's go ahead and get started. So imagine that you head on over to Home Depot, you're going to do a gardening project, and you buy 40 cubic feet of mulch for your garden. You plan to spread the mulch out to make a rectangular layer that is 3 inches thick. How many square feet can you cover? So here's one way we can figure that out is let's take our 40 cubic feet, so feet cubed, and divide it by one of its dimensions, the 3 inches thick, to figure out the area of the footprint of this rectangle. So one problem is that these have different units, so we'll convert the 3 inches to feet. 3 inches is 0.25 feet. All right, and now this is going to be equal to 160 square feet. A foot cancels out with a foot, and we're still left with square feet on top. So 150 square feet is the answer to the first part. Now, we said we wanted to spread this out in a rectangle, but we didn't say how long or how wide we want that rectangle to be. So what are some possible lengths and widths? So let's create a really tall table here, so leave lots of room. And I'm going to make it X and Y, but I will know that X will be the width and Y will be the length. So we can't make either of those equal to 0 because then the other side would become infinitely long. But we can do a really skinny 1 foot wide rectangle as long as we make the other dimension 160 feet long. So there 1 times 160 is still 160 square feet. All right, we could maybe go a little bit wider, go 2 feet wide, and now we can only go 80 feet long. If we come down to 4 times 40 is still 160. So notice how these still always multiply to be 160. We can go 10 and 16, or we can go 16 and 10. There's some other combinations in here, but I'm just trying to get enough. And then we can kind of reverse the whole table. So we could do 40 and 4, 80 and 2, 160 feet wide and only 1 foot long. And all of these still multiply to be 160. Let's take a graph of what this would look like. So if I make my rectangle very skinny, the other dimension can be very long, to the point where I guess if I was just laying out wood chip next to wood chip, I could probably go like several miles with my rectangle. And then if I make it very wide, the same thing happens in the other dimension. And we get a graph that looks like this. 1 comma 160 is over here, while 160 comma 1 is over here. And then in here, you get the numbers that are closer to each other, like 10 comma 16 and 16 comma 10. All right. Create an equation to relate L and W. So length times width must be equal to 160. Let's figure out what is the XY equivalent of this graph. So I said length was Y, width was X. And when we're graphing, we normally have Y by itself, so I'm going to divide X from both sides here. And you get that this is the graph Y equals 160 over X. All right, and when we have X in the denominator, we can get these really strange graphs that go off to infinity along a vertical asymptote as well as a horizontal asymptote. Goal for today is to use and recognize inverse variation. I said that backwards, but recognize and use inverse variation. Why are we doing this? It is one of the main 2 ways to describe the relationship between variables, but not everything falls underneath these 2 categories. There's plenty of variations that are neither direct nor inverse, but these are 2 very common ones. All right, so in direct variation, the X and Y pairs always divide to the same number. So what we can say is we have a constant quotient. All right, with inverse variation, the x and y pairs always multiply to be the same number. So we can say we have a constant product. All right, I would go ahead and pause and make sure you got all of this in your notes. The graph, the examples, everything. All right, sort the following into direct and inverse variation. So why don't you create a little table and we'll put all of these in there. So if they can be changed into y equals kx, that's going to be direct. And if they can be changed into xy equals k, that's going to be inverse. All right, so this first one, that's direct. That's already in y equals kx. And this one here, I could just divide that 3 over. My k value would now be 1/3. But what's important is just that x and y are just across from each other. Whenever that happens, it's still direct. So we're doing green for direct. All right, this next one, this is also direct. That divided by 3 could just be a coefficient of 1/3. So it doesn't really matter where the coefficient ends up. If we have an x and a y on opposite sides of an equal sign, and they're both on the same side of the fraction, it's going to be direct. That describes this one here, but not this one. And if I tried to move the x to the other side, it would be on the bottom of a fraction. They'd be diagonal from one another, so that would be inverse. Also, this one does match the inverse variation right there. All right, this one is also inverse. Constant quotient, I could multiply the y to both sides here, and I would see that this one is direct, this one is direct, and then these two are inverse. And I think this is every way you can combine an x, a y, and a 3 with either multiplication or division. Maybe you can come up with one more, but I think I got them all. So here's kind of one thing to help you keep these straight is write out the fraction x over y equals z over x, or z over w. Doesn't matter what variables you pick. But if you can ever get your fraction or your function to be a fraction equals a fraction, then you just look where the variables end up. If they are directly across from each other, like the x and the z, or the y and the w, or if they're right on top of each other, like x and y, z and w, those are all examples of direct variation. All right, if I change one, the other one will have to, let's say if I increase one, the other one will have to increase to keep everything else constant. So if x increases, z increases. If x increases, y increases. Now, if your variables end up diagonal from one another, that's when you get inverse variation. So that's inverse. And if one increases, the other one will have to decrease to compensate. The other spot that we see inverse is if two variables are right next to each other. So if I've got an x, y together in a fraction, that's inverse. All right, so what if I've got a table? How can I tell if I've got direct or inverse variation? Here's what we're going to do. We're first going to multiply pairs of x and y. All right, and when you do this, you'll either get a constant product each time, or you'll get a different product each time. If you get a constant product each time, then we can say constant product is inverse variation. All right, but if we got a different product each time, it means it could still be direct variation. So to test for direct variation, we're going to divide. pairs of x and y. All right, if we get a constant quotient, that's going to be direct variation. And if we get a different quotient each time, that's going to be now neither. And most relationships are neither. So don't be surprised if you are testing for direct and inverse variation and you have neither a constant product nor a constant quotient. All right, how are we going to remember this? Well, we're going to remember intellectual property for inverse product. So IP, or you can come up with your own thing. I'll say intellectual property. And then for direct variation is quotient, we'll remember Dairy Queen. So DQ, direct variation has a constant quotient. So intellectual property, Dairy Queen. And then if you can just remember one of them, then if it's not that one, then it's the other one. So to remember that direct variation has a constant quotient, just remember Dairy Queen. All right. So is this relationship between the variables direct variation, inverse variation, or neither? So let's check for constant product. So 2 times 15 is 30. 4 times 75 is 30. 10 times 3 is 30. 15 times 2 is 30. So intellectual property, this is inverse variation, because we have a constant product. All right, let's check this one. We'll check for constant product first. 2 times 10 is 20. 4 times 8 is 32. At this point, if these two don't match, doesn't matter what the other ones are. So this is not inverse. It could be direct. Let's check for a constant quotient. 2 divided by 10 is 0.2. 4 divided by 8 is 0.5. So we didn't get a constant quotient either. So this is a neither situation. All right. Now suppose we know that x and y vary inversely. And we also know that when x is equal to 4, y is equal to 12. So we know that because these vary inversely, they must have a constant product. So x times y must equal some constant k. Let's use this example to figure out what k is. So 4 times 12 equals k. 48 equals k. Now that we know k, let's rewrite our equation with the 48. So x times y equals 48. And that could be our function. We could also rewrite this as y equals 48 over x to make it easier to graph with the y being isolated. And now let's use our function. What is the x value when y is equal to 2? So I'll say x times 2 equals 48. And we divide both sides by 2. X equals 24. All right, so that x becomes 24 to keep the product equal to 48. 2 times 24 is equal to 48. Notice like the y value came down, so the x value had to go up. With direct variation, they both either go up together or down together. With inverse, when one goes up, the other goes down. All right. If the scale on a map is 1 inch equals 5 miles, how far does 4 inches on a map represent? Well, I think it's clear that this would be 20 miles, because 1 inch is 5, so 4 would be 20. Is this direct or inverse? This is direct. They were both going up by a constant amount. What's the constant of variation? It is 5, but let's give it the unit, miles per inch, which makes sense from that first one. 1 inch is 5 miles, so it's 5 miles per inch. And so then, 4 times 5 is 20 to keep that 5 constant. All right. So combined variations. We can have multiple variations within the same problem. And I think that diagram earlier where we did it like this is direct, this is inverse, is going to help us a lot. So direct, inverse. So let's turn this into fraction equals a fraction by just making it z over 1 equals kx over wy. And now we can make lots of different statements. We can say z and k vary directly. Z and w vary inversely. K and y, what are those? How do those vary? Well, that's this blue circle, the k and the y. They're vertical, so that is direct. And then the tricky one is when they're just right next to each other, that is inverse variation. So we could say w and y vary inversely. So I don't know how we could show that on a diagram, like another circle here to show that if they're together in one fraction, then it's inverse. Okay, and then so the whole idea is we're trying to keep this equation balanced, and what happens if we change one of the values? How does everything else respond? So if k goes up, then to keep everything balanced, x can go down, or w can also go up, or y can go up, or z can go up to keep everything balanced. Really important concepts here in physics, because you have equations with lots of variables, and you might just kind of wonder, if I increase one, how will the other ones respond? Will they go up or down? Okay, I'll embed a few more questions here. That's that for this lecture video. Have a good rest of your day.